This is the last offline lecture, lecture 24, and lecture 25 and lecture 26 will be recorded within a short time scale, and I will upload them on my YouTube channel next Monday in usual lecture slot, and also Wednesday lecture slot. So please watch the entire video and leave your message to check your attendance. Okay, so today's lecture will be devoted to a very important topic, quantum effect. So quantum effect is not very much discussed in undergraduate level course, but I wanted to devote at least one lecture hour to this very important effect, becoming more and more important nowadays. Before talking about quantum effect, let's just finalize our discussion on the device scaling. So maybe you remember I just categorized three errors for device scaling. One was Dennard scaling error, and in that case we just scale down planar MOSFET with geometric scattering. After that, now starting from certain 2000, so we have some problems in the geometric scattering. So the main driving force is switching from this to that was, from our current view, so that was actually gate current. Oxide thickness at the time was too much scaled, and the tunneling current through this extremely thin oxide layer was not negligible at all. So therefore we were not able to reduce this oxide thickness. So reduction of this scaling rule for T-ox is directly related with C-ox degradation. We do not get high enough C-ox value. However, we have to match our own current. This is the promise with our customers. So what we had done was to introduce certain ways to intentionally increase mobility by applying stress. So first we were able to meet the on current condition. After that, we solved that problem, T-ox problem, by introducing high K. So high K means that epsilon is around 20 or 22. In this case, although physical thickness becomes quite thick, like a 5 nanometer, but still we can keep it as very scaled, effective oxide layer. That was quite a big improvement, and even nowadays we are enjoying this high K metal stack. So maybe you remember, now the problem is, now we have silicon dioxide layer and silicon, and here we have a high K, and this entire stack, combination of silicon dioxide, native silicon dioxide layer, and high K material. These are taken as an overall dielectric layer. However, now the required thickness is approaching to the thickness of this native oxide. So that's the problem. It means that now we have no place to include sufficiently thick high K material. So C-ox scaling is nowadays once again a big problem. That was our final remarks on this era. So stress engineering error. Yes, so I remember that whenever I visit or I attend the conference, international conference on electronic devices, and at that time, during this period, the main focus was stress engineering. How can you apply even higher stress into our silicon channel? That was a serious research topic, and yes, we have enjoyed this kind of a thing quite a long time. Quite a long means that almost more than 10 years. Yes, we have enjoyed this one. However, when you go to about certain engineering node like 32 maybe, so I'm not quite sure it's the exact number, but 32 maybe. So now at around that era, even TSMC made certain huge difficulties for deliver good enough technology to their customers. So means that one single technical node was actually a disaster. So they completely failed to deliver working chip to their customers. Like who is customer? Like NVIDIA or other kind of Xilinx at the time. Those companies failed to get working chips, although they had a contract with TSMC. It means that now the end is approaching. So although they did their best to introduce a certain technological knob to improve the performance, but by keeping this planar structure, it became more and more evident that we cannot go further. So that was the situation of the end of 2010 around, and after that now FinFET came. Actually, the idea of FinFET was coined not 2010. Of course, it was proposed several years ago. I remember that when I was a graduate student, when I first heard about FinFET, the concept of FinFET, so actually the basic concept was proposed by researchers in UC Berkeley at the time. So I thought that that was a ridiculous idea, because in terms of its fabricational difficulties, that was too difficult at that time. So please think about the age or the time. It was around just early 21st century. However, at this point, we have no other options. So it became more and more clear that we cannot live with planar MOSFET. So that's the reason why we eventually move to the multi-gate structure. So the name fin comes from the some part of fish here. These are fins. So when they first observed the shape of this silicon layer, very narrow silicon layer, they thought that, oh, it looks like a fin. That's the reason why we call it as a fin. And when we have a look at the actual fin of our transistor, of course this is the very first version of FinFET, so you can see the clear difference. So what was silicon? This one is corresponding to the silicon. And now what is the silicon? The silicon just looks like this. So compared with the previous one, so now you can see that shape of a silicon area is completely different. So So that was the main reason we call it as FinFET. And basically, you know, this is a fin. This part is called as a fin, and this fin is covered by gate. And gate, when we make a close view of this structure, then now we can see that this is fin, and this is covered by high K layer, and after that we have another gate metal. So simply speaking, this gate is covering not just this top surface of our transistor, but also it covers this side wall and also side wall. So in terms of number of faces, when we consider it as a rectangle, then we can say that 3 faces are covered by gate. So that's the reason why the very first version of this FinFET realized by Intel was called as tri-gate. They named it as a tri-gate, but other companies just push or support the name FinFET. So nowadays everybody say just FinFET, but it's like a brand name of Intel version FinFET technology. So that was tri-gate, means that yes, so among 4 faces, 3 faces are covered by this gate material. So now even further, then double gate MOSFET. Double gate MOSFET is two faces are covered by gate. So let me just write down in this case. If this is a silicon material layer, then we wanted to introduce a certain gate, and on other gate here, then this gate will control these 2 side walls, and this structure is typically called as double gate MOS structure, because now we have two gates, and of course they are operated in the same way. The applied voltage for this right gate and left gate are identical, but anyway, now structurally we have 2 gates. So this is a double gate, and FinFET has more gate covering this top surface, so we call it as a tri-gate. And of course, if we push this trend further and further, so maybe you can ask me this question: is there quadruple gate? Yes, actually there exists quadruple gate, but no one call it as a quadruple gate, and this is nothing but the nanosheet we are currently fabricating. So in this case, now we have silicon once again, and this silicon is covered by high K material and gate for its all 4 surfaces. So if we follow this naming convention, maybe we can call it as a quadruple gate, but no one call it as this one, just to call it as a nanosheet. So please note that the reason why we call it as a nanosheet is its aspect ratio. Its aspect ratio is highly given here, so it is much wider. So in this case we call it as a sheet. And if we have the structure corresponding to the aspect ratio about 1:1, then maybe we call it as instead nano wire. But in practice, we are currently manufacturing only nanosheet devices, so just call it as a nanosheet. But anyway, so in terms of this structure, so maybe you can find that, okay, Tri-gate has more gates covered by gates, more silicon dioxide interface is controlled by the gate material. So that is actually the key factor of improved controllability of this FinFET. Simply speaking, FinFET is much better than its I'm going to say short channel immunity. It can make even shorter device without much problem. So I remember that I have heard about several discussion about this FinFET device. At that time, the common consensus was, although it was really difficult to fabricate it, however, once we can fabricate it, then it gives us much more technological freedom to make our device working well, because its architecture itself is much more superior than planar MOSFET. So we have many more rooms to improve the property. Okay. Anyway, so now you have seen the SEM image. So simply speaking, I think that I have discussed this topic once in a previous lecture, but let me just repeat it once again. If we wanted to, as a designer, if we wanted to have twice wider device, then what we had to do was just to draw twice wider silicon area. Then it is corresponding to the enlarged width value of my transistors. However, in the case of this FinFET technology, if I wanted to introduce a twice wider device, then actually I have to introduce another FinFET. Yes, that is the problem. So think about this one. How many fins are there? 1, 2, 3, 4, 5, 6. So we have 6 fins in this device. But if we have to double width, twice wider width, yes, then actually we have to introduce twice more fins. Scaling itself is just quantized. So therefore, number 2 increase. It is really okay. But however, if we wanted to make just 1.1 times wider device, 1.2 times wider device, can you make this kind of selection? It is not possible. So we were allowed to just have 1 fin, 2 fin, 3 fin. So that is really quantized. So that was at the beginning of this FinFET era, that was regarded as a disadvantage of a FinFET device. And now people are talking about, once again, nanosheet case. And in the nanosheet case, how can you control the width of a device? Yes, this is corresponding to the width of that device. So once again, we say that, technological guys say that now we have the freedom or ability to control our width once again. During the FinFET era, we had to select 1, 2, 3. There is just numbers, and we must select one of them. But now we can change it, the width more fully with nanosheet technology. Well, anyway, compared with the previous version, like against planar MOSFETs, so improvement was just amazing. So please have a look at this left side curve. So you can see that planar MOSFET and tri-gate, and this is nothing but So it's previous to the last planar technology. And you can see here the SS sub-threshold slopes are different. So you know here we have a certain slope, and here we have a certain slope. Let's just estimate what happens to this FinFET device. So I guess that this is corresponding to 10 to the minus 5, and this is corresponding to 10 to the minus 4. Yes, and this is corresponding to twice and 3 times. So now we have 3 orders of magnitude increase in its leakage current or sub-threshold region current. Then how much do you expect for these 3 orders of magnitude current deviation? So if that is really ideal, then maybe you can expect 0.18 volt difference in this case, because for each one order you need 60 millivolt. So let me just estimate it. So starting from here, now you can see that this is the result. I'm not quite sure I'm drawing the exact vertical line, because if I make any mistakes, then maybe I can overestimate or underestimate. But anyway, you can see that when we introduce 3 orders of magnitude difference in its current value, then what was it? So it was slightly higher than 2.2 volt. So it is corresponding to about 70 millivolt per decade or something like that. It's slightly higher. So then how about the planar MOSFET? It was even worse. So that's the reason why. So by just changing the architecture, so we were able to get this kind of a much steeper one. And what was the trick to have this much steeper one? So in the case of a FinFET, the fin itself is fully depleted. So you know what was the way to degrade this sub-threshold slope? In order to degrade this sub-threshold slope, in order to increase this SS value, you must introduce this M factor. So this M factor was the ratio between your depletion cap and oxide cap. If you don't have oxide cap, if you don't have a depletion cap, so the capacitance of your substrate, then M value will be quite close to number 0. That can be obtained by this FinFET technology, because basically this device is just fully depleted. There is no hole at all inside its fin region. So simply speaking, now since this is so good, so if we match, for example, the same op current, yes, let's say that what is the meaning of this matching op current? By matching op current, so we keep just stand by power as a constant. When you do nothing with your chip, when you just turn provide supply voltage to your chip, it consumes this IOP times your VDD values as a standby power, and it means that now when we have a given value of power consumption, standby power consumption, now you can see that clearly we have higher current value compared with this planar one. Well, maybe you can ask me this question. Well, although it looks slightly larger, higher, however, its difference is not that high, not that significant. No, it's not. Please, this is just to error of own current. In this case, we have to consider just percentage difference in its own current. So logarithmic change shown here is only good for what? Good for considering open current and sub-threshold slope. Small difference shown here really makes huge differences in its performance. So it is really great to have this FinFET technology. Or otherwise, if we match the off current or on current at, for example, certain gate voltage, then we can reduce the leakage current. It means that whether we improve the performance or whether we reduce the standard power, that is our choice. So by changing the threshold voltage of this technology, we can get certain technological advantages out of this FinFET technology. So once again, the scaling was survived. So here, by introducing this FinFET technology, although, how can I say, although the manufacturing this FinFET is much more difficult, but anyway they did it. And also from the viewpoint of analog guys or designers, circuit designers, they had to their ability to control width freely. However, anyway they survived, and now we have enjoyed once again this FinFET era about 15 years, and now we are here as of 2025. Even this FinFET, we were not able to reduce the device any further. Well, the very first version of FinFET was initiated from, in the case of Intel, its initial version was 22 nanometer. After that, it was reduced to 16 and 10, 7 something. And inside, between these major nodes, there are also some half nodes, like between 10 and 7, there was like a 8 node or something like that. So because it becomes more and more difficult to make the full change of our technology, so companies just slightly modify their design rule and says that, okay, this is 6 instead of expected 5, or between 5 and 3. So we have introduced also 4 nanometer node. This is a marginal change, not major change, minor change. But anyway, then how can they means that engineers can introduce so many different technologies? So just changing name. So I say that, oh, previously I called it as 10, but now I will call it as 7. So does it work? Actually, it doesn't work at all. Every technology node, they had to meet the requirement by the industry. There was a consensus. So the main way they did was like this. The main way was, at the beginning of FinFET era, the first fin just to look like this. This is the fin fabricated by Intel, and at its very first fin line. So every engineer in this field understood that the ideal form should be like this. How can I say, rectangular shape, is the one for our ideal shape. However, the first one at the time, please note that when FinFET was first introduced, except for Intel, nobody was able to fabricate it. And the only existing FinFET just looks like this red colored shape. So people thought that maybe they have some secrets for this fin shape. Maybe that was optimized. But in their second generation, they tried to make it more sharper. So this sloped fin was just a matter of fabricational difficulties. After that, they introduced a quite upright fin shape. During more than 10 years, people, engineers, always try to make it taller and narrower. So taller and narrower, by making taller, so we can increase its effective width quite a lot. So please note that it has quite high aspect ratio. So this is around a few nanometer, or in its final version, it's just a few nanometer, and this is corresponding to a few 10 nanometer. So this is really narrow and tall. So by increasing the height of this fin, we can effectively increase the width of this transistor quite easily. Then how can you make this taller device? So it is not that difficult. If you etch further, this additional etched height is just devoted to the height of your fin. So that was the trick. So always they just shrink the width of this fin and increase the height of this fin. And from the scaling property, more important part is this width. Please think about the shape. Now it is extremely scaled, and it is really tall and narrow. So simply speaking, the portion of this top surface is really negligible. The portion of this side wall. So although it is called as tri-gate, but among 3 gates, this top surface just takes a small portion, less than 10% or something like that, even smaller. So it can be just regarded as double gate structure. And if we have this double gate structure, most critical length scale simply becomes this width of this fin. And if we have narrower fin, this narrow fin gives us better short channel immunity. So with this short narrow fin, we can make our transistor shorter and shorter. So good. Starting from this quite a fat fin, so always they try to make it narrower and narrower. Finally, they arrived at the range of a few nanometer wide structure. But in that case, actually controlling the width became a real big problem, because they had to make an etch process. And how can you etch just nanometer wide fin uniformly in this structure? That became really big problem. So that's the reason why finally FinFET guys gave up at their 3 nanometer node, and starting from 2 nanometer node, they introduce a new way to define this silicon layer. So previously FinFET, in the case of FinFET, fin was defined as etching process. This part is etched away, and this part is etched away, and the remaining part is taken as a all silicon channel. But instead of this kind of etching process, now we just make atomically a thin layer, silicon layer, by ALD, atomic layer deposition. So this width control or thickness control becomes much more easier than previous etching case. So now, well, more or less silicon layer thickness is given, and that doesn't show much fluctuation. So that was the current situation. Okay, so I think that now, so people already have enjoyed this kind of architectural change quite a lot, so they wanted to push this kind of strategy further and further, but we have additional difficulties which should be overcome in near future. So always scaling, device scaling is one of the most important problem in semiconductor industry, and still we have more issues. Okay, so that was a short discussion about FinFET and the next generation technology. And now let's come back to our main lecture content, quantum effect. So today we will talk about quantum effect. I'm afraid that actually at the usual undergraduate levels course, this important quantum effect is just superficially discussed, but I would like to devote my lecture hours further and further. So I think that maybe I cannot finish this lecture contents in today's lecture. Maybe lecture 25, the recorded one, will be devoted to this quantum effect once again. Okay, so let me just start from this famous graph shown here. Although it is taken from Professor Tower's book, but there was a famous research paper about this quantum effect, and I'm not quite sure its exact year, but maybe if I remember correctly, it was 1974, something like that. So there was a engineers, not engineers, scientists, and they thought that actually the electrons in this MOS structure will experience a certain quantization effect, because the length scale of their potential well is so thin. I mean that this is angstrom, so 40 angstrom is corresponding to 4 nanometer, and this is corresponding to 8 nanometer. So although this MOS system at that time fabricated was just to have a quite deep substrate, several hundred micrometer, orders of 600 micrometer. However, the electrons are found only at just nearby 4 nanometer, something like that. So it is extremely much confined in this interface layer, and since this length scale is just a few nanometer, so scientists thought that it looks like a potential well. Which potential well? potential well generated by this one. What is this? This is the wall between silicon and silicon dioxide. So silicon dioxide has much higher conduction band compared with the conduction band of silicon. So from the viewpoint of electrons in silicon layer, so conduction band of silicon dioxide can be regarded as far away, much higher than its available energetic state. Please note that the energy range shown here is given as just milli electron volt. So since this is milli electron volt, a few electron volt higher, that should be regarded as infinitely high. So there was the perfect wall for this electron. And how about this right hand side? Of course, this is not a perfect wall, but it was made by the electric field. And by electric field, we have a certain conduction band H. What is this? This is nothing but minus Q times our electrostatic potential at position wise. By taking this number, what we get is just intrinsic Fermi level, and of course by adding approximately half of band gap energy, now we can pick up the point corresponding to the minimum conduction band energy. So this profile just shows conduction band energy, and it is highly confined. So therefore I'm just covering this part. Now from the viewpoint of our electrons, they can feel potential well formed by the oxide barrier, this left one, and silicon conduction band. This is given from its construction, its structure, and this one is not given by its structure. It is just electrically given. By changing your, how can I say, your applied gate voltage, now you can control the shape of a potential well. But anyway, it is true that there exists such kind of a potential well. Then the consequence is quite straightforward. So let me just come back to our elementary freshman physics course. Now think about this so-called infinite potential well problem. Maybe you have heard about this problem in your freshman physics course. So in this problem, we assume that at two boundaries, our wave function vanishes at this point and that point. After that, by solving Schrödinger equation, so now we can get the available allowed electronic state for our electrons. So the answer was quite simple. So when we consider its lowest available one, it just looks like a half of a sine function. And if we go to its second allowed energy level, then this is corresponding to a full period of a sine function. And if we go to even higher and higher index for our electronic states, then the trend is if n goes higher and higher, the corresponding energy is also increasing, and also the wave function shows rapid change in its physical or real space shape. So simply speaking, if it shows much variation in real space, it is corresponding to higher electronic energy. So that was the one we have studied in our previous freshman physics course. If you don't understand this one, then please leave. This is not that difficult, and I assume that all of you guys can solve Schrödinger equation analytically for some problems. So now we introduce this word, subband. Subband means that bands, but this is a sub-bands. So when we consider so conduction band of our silicon material, then we have a different hierarchy of electronic states. Means that if we just follow rigorous way for characterizing our available electronic states, what we have to do is to consider any arbitrary three-dimensional k-space. So k-space, k is corresponding to momentum. So just to consider three-dimensional momentum space. And in this momentum space, we can find that actually the silicon conduction band shows 6 minimas here and there. Why we have 6 minimas? Because we have 3 major axes, kx, ky, and kz, and due to symmetry, we have also one pair of minimum values like here, and exactly same distance and there, also here, and exactly same distance there, and also here we have exactly same distance there. So we have 6 copies of these minimum energies, and this each minimum energy point or the electronic structure nearby this minimum energy point, that is called as valley. So simply speaking, we say that silicon conduction band has 6 valleys and they are all identical in the case of relaxed silicon. So now we have 6 valleys. However, they have anisotropy. Means that, so although they are identical, let me just draw their iso energy surface. It looks like an ellipsoid, and their long axis is aligned to the principal axis. This is the one for this direction, and also we have another one aligned to that direction, and finally we have another one aligned along this vertical direction. We have 6 different bellies, and they have this kind of shape. Well, so when we talk about the silicon energy state, we have to say that, of course, an electron is corresponding to the conduction band is given, and which valley? First, we have to specify which valley is the valley belonging valley our electron, given electron is belonging to, and even this valley, we have this subband concept, because now we have potential where, since now we have a potential where the available states are quantized, so that's the reason why we introduce a concept of subbands. So simply speaking, so now our electron is following this valley, and even in this given valley, it can have the first subband, second subband, third subband, and so many other subbands are available. Why it is called as a sub-belly? Because well, this is just a convention, so we call it as a subbands. Means that this is not subbands, not from intrinsic material property, but this subband comes from the structural, geometrical, or electrical additional confinement introduce this further splitting of energy levels, and this is called as a subband. So how can you calculate this subband? So it's simple. In order to calculate this subband, we must solve Schrödinger equation, and by solving this Schrödinger equation, we can get available electronic states. So that was simple one. Maybe you can not understand what I'm saying right now, but let me just please allow me a few more minutes, and I will explain one by one. So before talking about the detailed structure to consider quantum effect in this case, let me just give you the significance of this consideration. Why we have to consider this quantization effect? It introduces huge difference in the expected electron profile. So please note that once again, although it is taken from Professor Tower's book, but the original plot was shown in the original paper in 1974, something like that. So here we have two different curves. Can you see it clearly? So this is classical, and what is it? Here we have quantum. So up to now we never considered the quantum effect. So up to now we have thought that electrons follow this shape. This red colored curve is corresponding to the position-wise electron profile. So it means that if we go to quite close to the real interface point, we will have quite high electron density. In this case, this is corresponding to the orders of 10 to the 19 per cubic centimeter. It means that at interface itself, maybe we have the electron density as high as 10 to the 19 per cubic centimeter. Well, it's not, in some sense, it's not that high. The peak electron density can be even higher, like 10 to the 20 or several times 10 to the 20. But point is, in reality, since this point is the really interface between silicon and silicon dioxide, so it is not allowed for our electrons actually found here. So simply speaking, by considering this quantum mechanical consideration, our electron density at x equal to 0 should almost vanish. Then what's wrong? Up to now we have considered quite high electron density at x equal 0, but now I'm saying that that's wrong. Our electron density should be 0 at that point. That introduces severe contradiction. How can you understand this contradiction? Yes, what is the truth? The truth is more close to this quantum mechanical one, and this is the real shape of our electron profile. So nearby this x equal to 0 point, it is really difficult to find electrons. then where can you find the electrons? We can find the electrons just on one or yes, about 1 point something nanometer away from this interface. Up to now, so what we have thought was, okay, here we have a silicon dioxide and now gate, and gate we apply quite a high gate. Oh, then all of our electrons are attracted by this high voltage. Oh, so they are attracted quite a lot, so they can be found at the interface. However, now think about this one. Here we have a little distance. So it is because if we really touch this interface, then it is not allowed by this boundary condition. So they just one step away from this silicon dioxide interface. So this is corresponding to the effect, main effect of this quantum mechanical consideration. So what's the matter? Is it really important? So previously, when we make our device quite large, actually it was not that important. So it's okay. But now we introduce extremely confined structure. So nowadays, even without this electrical confinement, think about your structure itself. Its thickness is, its nominal value is just 5 nanometer in our case. It means that even without performing any kind of electrical further confinement, so electrons are confined within 5 nanometer and their energetic state is already quantized, severely quantized in this case. So from the viewpoint of this gate material, gate contact, previously following classical description, they thought that, okay, since I attracted my electrons are just found exactly at the boundary. But when we consider additional physical consideration, quantum mechanical one, oh, because this is forbidden to exist, so now they are just found a little bit far from this interface. So please note that the main purpose of this MOS structure is changing gate voltage controls the number of electrons. That was the main one, and in this case important parameter was the distance between this guy, gate, and electron. So that was called as a T-ox, and by using this permittivity assigned to this material, intermediate material, we have introduced C-ox, epsilon ox divided by C-ox. That was related with the assumption that our electrons are found at the interface. However, in reality, electrons are found slightly away from this, how can I say, this interface. Then what happens? It is corresponding to that effective distance between the gate and electronic gas should be a little bit higher than physical distance of our oxide layer. Okay, so electrons are found there, so therefore in order to change their numbers, the effective oxide thickness is not simply given as this only contribution from oxide, but we have to consider additional distance coming from quantum mechanical electron distribution. So of course this is a long discussion, but I wanted to just deliver in a digestive way. So simply speaking, the COX value simply generated by oxide thickness is not perfectly matching the effect or movement or behavior of our electrons. We have to consider additional component, additional distance, and since the distance is increased, what you can expect is this considering quantum effect is not involved with higher COX. No, it is involved with lower COX. So bad effect is related with this quantum effect. Okay, so simply speaking, here effective gate oxide thickness becomes larger than its expected value of TOX. Usually people think that increase of effective thickness is not like 5 nanometer, 10 nanometer. It's like just point something nanometer is increased by this oxide. So it's a quantum mechanical consideration. Well, point something nanometer. This is just corresponding to orders of angstrom, so it doesn't make big deal. But please remember that in our previous 90 nanometer technology, the scaling, that serious problem was occurred because we were not able to reduce our oxide thickness down to 1.05. They fail and they just introduce 1.2. So that was the starting point of all of this quite complicated discussion. So simply means that this angstrom scale difference in TOX is critically important, so we must consider this effect. Okay, then maybe you can ask me this question. Well, Professor, up to now we have lived without this kind of this important consideration. So, is every discussion we made up to now is wrong? It really depends. If we consider just terminal behavior, still we can live with the Pausa expression. Oh, why? We have different COX value. Our COX value is now long. Yes, your value is long, but the way is we just slightly change COX value to match our observed behavior. So since in this case we have so many unknown variables and we are just doing improving the performance of our transistors, so we have to live with a kind of uncertainty in our parameters. So still our previous discussions gives us valuable expressions for terminal characteristics. It's completely okay. Just to regard this new knowledge or new understanding on this quantum correction as an additional improved knowledge on your device physics. All of your previous study is not meaningless, but it is really meaningful. So anyway, now you can understand quantum effect introduce increase of COX. So therefore, now it can introduce many things in our case. So now let me just start more detailed discussion. In order to analyze this problem more exactly, actually what we have to do is to introduce numerical solver. You need a computer program. This program is called as Schrödinger-Poisson equation or Poisson-Schrödinger equation solver. Anyway, the appearance order is not important. Means that we have to solve a Poisson equation. Yes, we have solved Poisson equation that is given. Additionally, we have to solve Schrödinger equation. So if you are interested, maybe you can watch my YouTube videos. So there are series of three videos, but it will take some time. Well, so it is known way to analyze this solvent structure, but the scope of our lecture in this semester is not developing numerical tools to analyze something, just to understand more intuitive way or analytic way. So we have to go to this approximation. By the way, if you are interested with this kind of thing, then maybe in next semester I will open another course for devoted to the development of numerical course. So please enroll that course. But anyway, let's just come back to our main discussion. In this case, we have to live with approximations. Then how can we approximate our potential well? Simply speaking, we can introduce triangular potential well approximation. Is it really triangular? So when you have a look at this curve, can you expect this is triangular? Well, certainly we have this behavior, and if we just consider depletion approximation, then solution of our potential always follow this quadratic form, because there is no, how can I say, there is no electronic contribution and no Hall contribution, and also only from doping density, and we usually assume constant doping density, so it introduces a parabolic potential well. So if I have to say, then the first trial will be parabolic potential well, but it does not give us a proper approximation. So instead, linear one is taken. So simply speaking, the general shape of our potential well just looks like this kind of a parabolic one. However, instead of considering this long range behavior of our potential well, we will just concentrate on this interfacial behavior. In this case, of course, we can always take this normal gradient and takes this gradient by using the linear approximation that is given as this one. So simply speaking, how can you build this kind of linear profile? We just take surface electric field, and by using this surface electric field, we can draw just a straight potential well line. So let me just give you this discussion. Well, let's say, although we have assumed this straight line, let's assume that our real shape does not follow, and it just looks like this parabolic way. Then what is our problem? Now we have strong error, or very large error at this point. So therefore, the solution of our Schrödinger equation with this linear or triangular potential well and this parabolic potential well will differ. However, please note that when we have this potential well, where can you find the electrons? Electrons are only found the deepest side of our potential well. So our electrons are only found here. And how about this point where we have high error in our potential? There almost no electronic wave function is found. So although we introduce errors in our potential well, but when we actually solve this problem, our solution, the electronic wave function, does not touch that erratic point. So that's the reason why we can believe that even by solving this triangular potential well with some errors in deep substrate, but it doesn't matter because our solution is always just determined by the, the interfacial potential problem. So that is the assumption we have made. Okay, it's 10:15, so I have to stop now. So now we have two more chances to meet each other through YouTube videos. So lecture 25 will be recorded probably tomorrow morning in this classroom, but you don't have to come to this lecture room. I will just make a normal lecture and open it next Monday, and 26 will be open to you the Wednesday. So and as I told you before, our final examination will be June 16th, and style or time duration, everything will be quite similar to that of midterm examination. Thank you for your concentration during your effort during this semester, and let's have a look. Let's meet again in second next Monday. Thank you.